example 1, we were given this graph and you're required to find delta h12, and they say you're given h is a function of t and v. H is a function of t and v. And then you're given point 1, point 1, point 3, point 2. Right. There you go. How am I going to find delta h12? Right, I can, so in the surface, delta h12, I could go from 1 to 2, or I can go 1 to 3, where I keep t constant at, this is t1. And then I change v, and then afterwards I can go to 3 to 2 and keep v constant at v2 and and change t, because it will go from t1 to t2. Okay, so that's one way. And then another way is maybe, wait a minute, I can, part B, I can actually go to point 4. There's other options, and keep v constant at v1 and then travel to point 2, keeping t constant at t2. So you have different options to get there. So would path 1, would path A be the same as path B? I think maybe your question lies in yes, it will be, if and only if it's an exact function. So you go, okay, mathematically, how do I do this? Okay, so I know graphically where to go. So mathematically you go, okay, h is a function of t and v. Fine, so maybe I can write the total differential dh by dt, where h is a function of t, keeping v constant, to dt, plus the partial derivative of h by dv, where h is a function of v, keeping t constant, dv. And you're okay, I can't go any further than this. I can't really integrate my I don't know my differentials. You know, but wait a minute, they gave me the definition of the function for this particular system. They gave me that h equals t squared over v. And you, oh, okay, that's great. So then, therefore, the partial dh by dt, tv, keeping v constant is, okay, what is 2t over v. And from equation 1, my dh by dv, keeping where h is a function of t and v, keeping t constant, is minus 2 squared over v squared. Okay. What do I do next? Okay, I can substitute it in. Substitute the above into 1. Therefore, my dh is equal to, 2t over v dt minus t squared over v squared dv. You go, oh, nice. And if I introduce integrals 1 to 2, and I can integrate, I should be able to integrate both sides. But I don't know my TV combination. So these are variables, right? These are variables. So you go, okay, well, at least I know I can say that delta h12 is equal to the integral of 2t over v dt minus t squared over v squared dv. And I'm going to take it to some sort of tv combination. But what is this equation here telling me? Okay. Or actually, yeah. If I come here and I take this one, or if I take this equation, if I take this very equation, yeah, let me just start again. If I take this equation, dh is equal to 2t over v dt minus t squared over v squared dv. What is this? This is, say, equation 2, right? What is this equation here? This is the one I want to focus on. What's it saying? Well, it's saying that I managed to get my total derivative and then I substituted in for my partials, for the actual, what the function represents in the system. You go, oh, okay, so that's what my dh is. So you're saying if I integrate between any point, I'll be able to get my dh. Yes, because this equation here for this particular system represents where you can get a dh between point 1 and 2, depending on where your integrals are. So between 1 and 2, or between 2 and 3, or between 2 and 4. You go, oh wow, that's actually this total differential. Once I know my function, what is defined in this system, I can actually find the delta h of this system, or this delta h between 2 points. If I keep v constant, you go, yes, exactly, that's how powerful the total differential is. And then you go, okay, right, so fine. So for path A, what did we say? So for path A, delta h 1, 2 is equal to delta h 1, 3 plus delta h 1, 3, 2. Sorry, delta h 3, 2. So in delta h 1, 3, it's going to be 2t over v dt minus t squared over v2 dv, okay, plus my delta, and then plus my delta h v32, which is also equal to 2t over v dt minus t squared over v squared dv. Okay, but I still need to integrate these, and I still need to integrate it, and I still need to evaluate it. So, but what did we say for delta h 1, 3? So 1, 3, we said from point 1 to 1.3, we said v, t is constant, but v changes. Okay, so that means from path 1 to 3, my delta h for that is t is constant. So therefore I got minus t squared over v squared dv. Okay, that's fine. And then going up from 3 to 2, what does that mean? From 3 to 2, that means t is changing but v is constant. So then that means I've got plus the integral, of 2t over v dt. Right. So remember, this section belonged here, and this section belonged here, and then this section came from here, and this section came from here. All we said is on path h32, v was constant. That meant dv equals 0. And then we said on path h312, what did we say? T was constant, and then that implied that dt equals 0. And then you can find delta h12 is equal to, you will find it once you integrate it and substitute it in, well, is equal to negative, so t squared over v squared dv plus 2t over v dt. So where am I taking my dv from? From taking it from v1 to v2. Okay, so because this is v1 and this is v2, v1 and v2. And then for my t in the second part, I'm taking it from t1 to t2. But wait a minute, b, what about b? Oh, b is quite similar. I can use the universal equation, equation 2, but like b, h12 was equal to delta h, 1 goes to 4, plus delta h, 1 goes to 4 goes to 2. So 1 goes to 4 and 4 goes to 2. Okay, path, oh, so, sorry, that's, yeah, I named it. So actually this was supposed to be, excuse me, this was supposed to be path B, and this is path A. Whatever, as long as we're following the numbers, we're still fine over there. Right, so delta H14, it's okay, what is it? It's the integral. So, okay, it's the integral of 2t over v dt minus the integral of t squared over v squared dv. I'm using the same equation, so this is delta H14, and I still need to evaluate it, so I'll have to put in those, but I don't know yet, plus the delta plus the integral of 2t over v dt minus t squared over v squared dv. Right, what do I do? Okay, from 1 to 4, if we recall, from, so here's our graph, from 1 to 4, t1, t2. So v was kept constant. V was kept constant, v1. So that means v is 0. So equals the integral from t1 to t2 2t dt, and actually v1 was kept constant. So you can actually substitute in for this variable v1. Plus what happened, so this was from 4 to 2. So from point 4 to point 2, my v's changed, but my t was constant at t2. So if my t was constant, I mean this term cancels up, and then I traveled from v1 to v2, and that's a negative. And then what do I get? I have to evaluate it at t2 squared over v squared. So I have to integrate for dv. And then that's your delta H12 for 2 different paths. Yeah, if you want to know what, maybe you would have picked it up, where would I have evaluated this from? This is from t1 squared, and then for, so over here, and then for here, for if we're just looking, sorry, back at part B, I forgot to put in forward my variables here. What v is this? V in part 2 is, my v was constant, so that is v2. So you put in v2 there. Okay, so at least do it graphically first, and you can see what must be kept constant and what must change, and you'll find for exact functions it doesn't depend on the path, you'll eventually get the same delta H2s. Right, and you could choose either way you want to go, just like with the notation. You can just choose if you want to go on path A or path B. And here you integrate with respect to t, with respect to v, with respect to t, so depending on which path you want to go. But as you can see, like here, maybe you'd want to, if you want, like, your total differential is your basis for everything, and what you do from there is you can, if you know more information about the definition of the function, what it represents for a particular system, you can substitute it in and find your answers for. So this was an example of a system that follows that function. Okay, so it has that particular shape, but you know you have an HTV space, or whichever axis you look on it, and in that TV space you will be able to find your delta H. And that is the beauty of differences and integrals and how exact functions come into play. And this is the real application. The notation, manipulating, it just helps you to manipulate your equations to use the thermodynamic equations. But this is an example of actually using it to use in, probably, for example, if you consider H to be enthalpy, to use it in energy balances to find your enthalpy of your process.